So in classical physics, both particles and waves are mutually exclusive. So for particles, they're point-like masses which move along a trajectory in 3D space, and the position x and the velocity v can be determined with an arbitrarily high precision at any time. So you have your function x of t, and by differentiating that you can get v of t, and by differentiating v of t you can get acceleration as a function of time, a of t, and by x of t you can model the velocity, acceleration, energy, and momentum of a particle in this classical system. So your time evolution is perfectly predictable from the classical equations of motion. That includes Newton's laws of motion, and your kinematics equations. Because of this, you can say that in everyday life you only experience classical mechanics. You have a definite position and momentum. It's very localized and it's deterministic in nature. You have your functions and the laws predict exactly what's going to happen next in the future. You also have waves. Waves are not localized in space. There's no mass associated with a wave. It's a propagating disturbance that propagates energy, that essentially carries energy within the medium, or in the case of EM waves, without a medium. The energy is stored in the fields. It has a characteristic wavelength or frequency, and it propagates with the speed v phase. So those are particles and waves, two separate phenomena in classical physics. However, classical physics fails in the relativistic domain, so at very high speeds, near the speed of light, where Einstein's theory of relativity works, and most importantly here for this video, in the microscopic domain. So the stability of atoms and the properties of subatomic particles could not be explained using rigid classical ideas. This includes black body radiation, the photoelectric effect, and Compton scattering. This is where quantum mechanics comes in. Quantum mechanics deals with quantum objects. Quantum objects are very small and imperceivable to our human experience. We usually say that they are in the quantum realm. So there's no exclusive particle or wave identity for quantum objects. They both have wave and particle-like behavior, but they're not both particles and waves. They're quantum objects. They just have particle and wave behavior that they can be modeled using particle and wave behavior. These quantum objects are modeled by a wave function and mathematics. It's highly mathematical. And because they have that wave-particle duality nature in them, they are not completely localized. This means quantum mechanics is probabilistic in nature. It's not deterministic like classical mechanics. It's probabilistic. It only gives you probabilities, and probability is closer to nature. We can only predict outcomes, which is much more realistic than saying exactly, hey, at this time this particle is going to be there. Like it's much more accurate to real life and to the characteristics of nature. Remember, nature has no duty, no responsibility of making sense to the human perception. So at the quantum level, the effects can be counterintuitive. Objects can have both wave and particle-like nature. It's our duty to understand how nature works, not the other way around. Nature does not have to make sense to us. So it's biased towards nature. So essentially it's discrete. quantum mechanics deals with discrete values, so you have discrete energies, you have quantized energies. And essentially, all quantum mechanics has to offer is statistical info about possible results. So, there's a famous saying that God throws dice. It's saying quantum mechanics is suggesting that nature is probabilistic on the fundamental level. So let us explore some of these quantum ideas. So essentially, you have particle and waves. So essentially, you have particle and wave-like behavior. For what was classically thought as waves, such as EM radiation, electromagnetic radiation, was now in the quantum realm thought as a stream of particles, so photons, each with energy h nu. Similarly, if matter were considered as particles in classical mechanics, because of the symmetry of nature, they too should have waves constituting them, matter waves. This was a hypothesis suggested by a French scientist named de Broglie, hence named de Broglie hypothesis. It was proved experimentally, but not mathematically, these matter waves. So essentially, de Broglie hypothesis is that matter waves describe the wave-like properties of quantum objects like electrons and electrons and protons when they are confined to dimensions on the order of the size of an atom. Essentially, nature loves symmetry. Since the radiation or electromagnetic waves behaves like a particle under suitable circumstances, the particles should behave like waves under particular circumstances as well. So essentially, what de Broglie did was he took the energy of a photon, h nu, and equated it to the relativistic energy from Einstein's theory of relativity. And since photons get their energy from their momentum, the rest mass of a photon is zero. That means a photon cannot exist as it stands still. A photon has energy because it has momentum. So that means energy equals h nu, which equals the momentum times the speed of light, pc. So h nu could be equated to pc, and if the energy of photon is h nu equal to pc, we can turn the nu in terms of lambda. So from the photoelectric effect, we can say hc divided by lambda is equal to p times c. Now, if we solve for our wavelength, we get wavelength is equal to h by p. And if we solve for momentum, we get p is equal to h by lambda. So this was for photons. This is the wavelength of a photon according to its momentum. The more momentum a photon had, it had more energy. Therefore, it had a smaller wavelength. If we extrapolated this to any moving object having a momentum p, like in matter waves, we get p equals h by lambda. So, according to this relation, if a particle of mass m has a greater momentum, that means its wavelength should be smaller. And if it has smaller momentum, that means its wavelength should be larger. Wavelength of what exactly? Wavelength of the matter wave. The matter wave that describes the matter, essentially, the particle. Remember, particle, if radiation waves behaves like a particle under suitable circumstances, particles should also behave like waves under particular circumstances. And this was proven by the Davison-Germer experiment, where electrons were accelerated such that they had a wavelength similar to that of the lattice spacing in an atom. I think it was graphite they used in a crystal of graphite, and the electrons were scattered onto the surface, and they scattered off the surface, and they interfered with each other. And that showed that electrons can behave like waves, and that thus proved the existence of matter waves. But what exactly is waving in a matter wave? What is periodically changing in the case of matter waves? So in the wave equation, there's something u that is changing. So in the case of a wave on a string, it's the displacement, the height of the wave. In EM waves, it's the electric and magnetic field densities that are changing. What is periodically changing in matter waves? That is unknown. It's a mathematical entity related to certain physical entities. We don't exactly know what it is, but that does not mean it is not useful. It is useful. It's called the wave function. It's a mathematical entity. And if we take the 3D wave equation with the Laplacian, we can substitute the wave function psi, that's a simple psi, into u, and we can see how this matter wave evolves with respect to time and position. So recall that we have our de Broglie wavelength for our matter wave. The wavelength is inversely proportional to the momentum. We have our psi, which is the wave function that changes periodically to constitute the matter waves. Again, mathematical entity. If we apply that to our wave equation, our classical wave equation, we get this equation. Remember, this is in 3D, for 3 dimensions. By applying de Broglie's relation to this classical wave equation, we can arrive at the Schrödinger wave equation, which tells us about the properties of our matter wave and how it evolves with space and time. These are very important parameters for describing our quantum system and understanding how our quantum system evolves over time. Just like how in classical mechanics we used Newton's laws of motion to find the position function x of t and do useful things like differentiate it and get the velocity with respect to time and acceleration with respect to time and energy with respect to time. Similarly, we use the wave function that changes periodically, this mathematical entity, to find properties about our quantum system, about our particle, and calculate probabilities of position, of momentum, and find other useful properties of the system, and also describe how the system evolves with respect to time. Before we tackle the Schrödinger equation, it's important to understand a byproduct of this wave-particle duality for matter waves, something called the uncertainty principle. Say you have the harmonic matter wave given by psi is equal to psi naught sine of omega t minus kx. Suppose this is your equation for the matter wave. You have a sinusoidal wave that extends from negative infinity to positive infinity. This means that the position is delocalized. It has no definite position. The particle, remember, this is a matter wave, it describes a particle, and the particle has no definite position. However, the frequency of this wave is fixed. Ignoring my slightly off drawing, you can see that it has a constant wavelength, and by using the wave relation, the frequency is just the speed of the wave, the phase velocity of the wave, divided by your frequency. The frequency is just the wavelength is the phase velocity divided by frequency. So we can say that has a constant wavelength, and by de Broglie's relation, we know that if it has a constant wavelength, the wave has a constant momentum. It has a constant momentum. So you can see that the particle is completely delocalized. There's no definite position. However, it has a definite momentum because the wavelength is exact. So essentially, by fixing nu, the frequency, we fix the p. However, because we fix the p, we don't know where the particle x is. The particle is completely delocalized. The uncertainty in the position along x comes at the cost of the certainty in momentum along x. So let's say we try to increase some of the uncertainty so we can get an idea of where the particle is. So what we can do is we can add up a group of waves with slightly varying frequencies. So nu is equal to nu plus or minus a little bit of delta nu. That means there's a little bit of uncertainty in the momentum as well. So p would become p plus or minus delta p. And that creates something called a wave packet. When those waves are added up, it creates this packet of a wave. So we went from a sinusoidal wave that is completely delocalized to a matter wave that's something like this. That means we know better that the particle should be somewhere over here rather than here where it's completely delocalized. We did that by changing the frequency, by adding up a little bit more different frequencies so we can get a wave packet. But by doing that, we increase the uncertainty in momentum. So by trying to decrease the uncertainty in position, we increase the uncertainty in momentum by adding more different waves. And this is just a fundamental reality of these quantum objects because they display wave-like behavior as well. So for matter waves, this applies. So it becomes impossible to specify the position and momentum along the same direction of the particle with arbitrary accuracy and infinite precision. It's inherent in nature of quantum objects. If you have a sinusoidal wave with a fixed frequency, you have a fixed momentum then. So your delta p is 0. But because its fixed frequency extends all the way from negative infinity to positive infinity, so the uncertainty in your position is infinite. If you decide to make wave packets by adding in a few more waves of slightly different frequencies, you decrease the uncertainty in position, but by doing so you increase the uncertainty in momentum. So we know that the particle might be over here somewhere or by over here somewhere. But now we know less about the momentum of the particle. And if we continue to add more and more and more waves, we reach a point where the matter wave collapses, the wave function collapses right here, and you know exactly where the position of the particle is, but because you added so many different waves of differing frequencies and created this huge wave packet, your uncertainty in momentum becomes infinite because you added all those frequencies together. Remember, like this. So then you arrive at an inequality where your uncertainty in momentum and uncertainty in position multiplied together is greater than or equal to h bar by 2. H bar is just Planck's constant divided by 2 pi. And this is called Heisenberg's uncertainty principle. So you cannot reduce a particle like an electron to a particle like determinancy, as it also shows wave behavior. And this just, again, it's inherent in nature of quantum objects because they display both wave-like and particle-like behavior. So we now understand what the wave function is. The wave function is a mathematical entity again. It directly has no physical significance. It's just it describes the behavior of matter waves. It constitutes matter waves, and it's the wave function that describes the properties and the probabilistic nature of the quantum system. The periodic variation of this quantity psi constitutes matter waves. It's what's waving in matter waves, and it is a complex function. So it has a real term and an imaginary term. So if we decide to take the magnitude of the psi function and square it, that's equivalent to taking the complex conjugate of psi and multiplying it by psi, and that results in probability density. Psi itself has no meaning, but if we multiply it by its complex conjugate, that results in probability density. That tells the probability of finding the particle within a given region. If we are considering 3D space, then it's proportional to the probability of finding a particle in an infinitesimally small volume dx, dy, dz. So if this entire volume, it's the probability of finding the particle in that small volume. Of course, we'll keep it simple and deal with the linear case first, where the particle is confined to move in only one direction along the x-axis. And if we take those probability densities and integrate them between two boundaries, negative a to a, we can find the probability of finding the particle between negative a and a. We're essentially squaring the wave function, and by squaring the wave function, and we get the probability density function, and by integrating between two boundaries, we get the probability density. That's the probability of finding the particle between negative a to a. Of course, in order to do this properly, we need to make the wave function normalized. That means we always need to normalize the wave function. That means that when we integrate from negative infinity to positive infinity, the entire probability must be 1, because the particle can exist anywhere in that range. Because it can exist anywhere in that range, it must, because the particle is there. If it's not 1, that means the particle does not exist everywhere in possible places. It just means that the particle exists. The probability of finding the particle in the universe must equal to 1, else the particle does not exist. So we must always normalize the wave function, and that ensures that psi describes a valid physical state and makes the calculations meaningful. If psi is not normalized, we must normalize it by adding a constant. So if it's not equal to 1, it's probably a variable, a constant a times 1. So if we take the normalized function psi prime, we can add a normalization constant n, and then when we take the magnitude of it and square it and make it equal to 1, we can factor out the magnitude of the squared of the constant, the normalization constant, and that ensures that our wave function is normalized and we can calculate probabilities effectively. For example, if we consider a particle trapped in an infinite potential well, we can see that the psi for different energy levels, so n1, n2, and equal to 3, and equal to 2, and equal to 1. This is the psi function, which essentially becomes the standing wave trapped between these infinite potential boundaries. But if we plot the psi squared, we get the probability density function. And by integrating, say, from here to here, we can find the probability of finding the particle in that region. In some places, the probability density drops to 0. That means there's 0% chance of finding the particle here. And at the boundaries too, that means the particle must exist within this well and cannot escape the well. Now that we know about the wave function and how it's describing, it's a mathematical entity describing the state of the quantum system, and from the classical wave equation, and how the evolution of this wave function is what constitutes matter waves, and from de Broglie's hypothesis saying that matter waves can have a wavelength, particles can have a wavelength dependent on their momentum, we can arrive at the Schrödinger equation. The Schrödinger equation is essentially the Newton's laws for the quantum system. In a sense, it's not exactly, but it's just as important. It predicts the dynamics of non-relativistic quantum mechanical systems using the wave function psi. We can use it to solve and find psi. Then, using psi, we can predict analytically and predict precisely the probability of events, like I said before. Before I move on to the derivation of the Schrödinger equation, it's important to understand the difference between an eigenfunction, eigenvalue, and an eigenoperator. The eigenfunction is your wave function, that mathematical entity that describes the state of your quantum system. Embedded in it are the probabilistic natures of the quantum system, and to extract information from the eigenfunction, such as energy, such as position, such as momentum, we operate on the eigenfunction using an eigenoperator. An eigenoperator is a specific operator acting on an eigenfunction to extract physical information about the system. And by operating on the eigenfunction using an eigenoperator, we get an eigenvalue. The eigenvalue is the measurable quantity of the state of the system. So if we operate this is called the Hamiltonian operator. If we operate the Hamiltonian operator on the eigenfunction, we get the energy of the system. So that can be an eigenvalue. In the case of the Hamiltonian operator, there's a momentum operator, there's different types of operators, but we'll focus on the energy operator for the derivation of the Schrödinger equation. So there are two different types of the Schrödinger equation. There's the time-dependent type and time-independent Schrödinger equation. We'll focus on deriving the time-dependent Schrödinger equation first, then we can move on to making it time-independent. So it's easier for problems where time evolution is not as important as spatial evolution. Okay, to derive the time-dependent Schrödinger equation, we first take the wave function given in this form, and we differentiate it with respect to x, partially differentiate, because it's a multivariable function. And then we get ik e to the I kx minus omega t, and that just becomes the function itself multiplied by I times k. If we take the second derivative, partial derivative with respect to x, we get ik twice times the function, which can become I times I becomes negative 1, and k times k becomes k squared. And if we recall, the wave number is 2 pi by lambda. Using De Broglie's hypothesis, we can relate the wavelength and momentum of the particle, and by merging the lambda and lambda together, we can get a quantum expression for the momentum in terms of the wave number. And this is that expression, P equals h bar by k, and that's for 1D. and 3D it's a vector, where this is the wave vector and this is the wave number. If we substitute this into our original expression, we get the second derivative of the wave function is equal to negative p squared by h bar squared times the wave function. We can move the p squared to the other side, and we get p squared times the wave function is equal to negative h bar squared times the second partial derivative of the wave function. Now, if the particle is experiencing a potential v of x, usually potential wells do not change with respect to time, so we're taking that assumption. If a particle is experiencing a potential v of x, then the total energy of the particle would be the kinetic energy in terms of momentum plus the potential energy v of x in the potential well. Then we multiply the wave function on both sides of the equation, and this is where things get interesting. We can then substitute the momentum in terms of the expression we derived earlier, right here. We can substitute that expression, and by substituting that expression, we can then do something that would upset many mathematicians, but we're physicists, so what we're going to do is we factor out the wave function itself, and that clumps together all the operators, and we can condense this into a single operator called the Hamiltonian operator, which is represented by h cap. Remember, operators operate on the wave function to extract information. In this case, the Hamiltonian operator operates on the wave function to extract information about the energy from the wave function. And then we can also derive an expression for, just like how we did with energy, we can derive an expression using the frequency of the matter wave. We can derive an expression for the energy of the particle, which is just h bar times the angular frequency of the matter wave. Now, if we this time differentiate the wave function with respect to time, partially differentiate with respect to time, we get this expression right here, negative I times e over h bar times the wave function. And if we rearrange to get e times 5, e times the wave function 5, we get this expression right here, which eventually all equals I times h times the partial derivative of wave function with respect to time. And if we substitute that back into our expression instead of the energy times the wave function, we substitute this, we get Schrodinger's time-dependent equation in its full glory. And this is right here, that's the del operator, the nabla operator, and that's for 3 dimensions. In the single dimensional case, that would be just d squared by partial d squared by partial dx squared. And replacing it with the operator Replacing it with the eigen operator, we can condense this equation further. We can say that the Hamiltonian operator operates on the wave function to get an eigenvalue, the eigenenergy out from the wave function. And that's your eigenvalue equation. So to get to the time-dependent Schrodinger equation, because sometimes we're not interested in the evolution of the wave function with respect to time, we can derive the time-independent Schrodinger equation. To do that, we first separate the wave function into two separate functions of spatial evolution and the temporal evolution. Significance. Then what we do is we plug that into the time-dependent Schrodinger equation, like so. And then afterwards we can distribute the operators on both sides. After distributing, we can clump together this operator right here, which is your Hamiltonian, and then we can divide both sides by the XLT, which moves all the time-dependent terms on to the right side. And to balance that out, we divide the spatial term over here, the 5x. Here, we move it here, but we cannot cancel it out. But what we recognize is that this becomes the energy operator times the time-dependent function of the wave function, and that is a constant because the time is stationary when we're considering the time-independent Schrodinger equation. Next we can, since we know this is the energy operator and that's constant at that given time, the energy is constant and not changing, we can move the energy to this, we can move the XLT to this side. Then after doing a little bit of more mathematical operations and rearrangement, we can arrive at a position where we can integrate both sides and get this exponential decay function. And with that, we arrive at the time-independent Schrodinger equation, where this is your Hamiltonian operator times the wave function, which is only spatially dependent, is equal to the energy times the spatially dependent term. This is much more useful to us and much more simpler to deal with, since the wave function is stationary with respect to time, and it's not a multivariable function but rather a single variable function. That is the time-independent Schrodinger equation. In this case, the wave equation becomes reduced to this form right here, where c is the constant that comes from integration. So 5 of x is your spatial dependent portion of the wave equation, and where e is your energy value, t is your time, and h bar is your reduced Planck's constant. We can further simplify it to this, where instead of the energy and the h bar, we can use the relation we derived earlier right here and substitute it, so it's in terms of the angular frequency omega. So we are left with three equations: the time-dependent Schrodinger equation, which shows how the quantum system evolves with respect to time. We have the time-independent Schrodinger equation, which tells how the system evolves with the fixed time, and how the wave function evolves spatially. And then we have the eigenvalue equation, which is just that but simplified. So essentially, the Schrodinger equation, it constrains the wave function and describes the evolution of the wave function with respect to space and time. If we take a look at the time-dependent Schrodinger equation, you can see uh, how the energy total stays the same. But this operator operates on the wave function, and thus the quantum state psi, is changing with respect to time in a very specific way depending on the total energy of the system. This allows us to predict how a quantum system should behave if we can mathematically write down all the energy present in a system. And here's a little bit more about the Hamiltonian operator if you're interested. It essentially it's a mathematical description of the total energy of the system, and it operates on the wave function to show how the quantum system evolves, how the energy of the system is evolving. It's an operator, it operates. To summarize, in quantum mechanics, we find psi as a function, the wave function of a particle, and if we, as I said, take the square of it, absolute value and square of it, it gives the probability of finding the particle between at time t between two bounds, which we do in the integral, and it's a statistical interpretation of psi, and it introduces indeterminacy. In other words, even if you know everything about the theory on the particle, such as the function, essentially the wave function psi, we still can't predict everything with certainty of outcome of the simple experiment, such as to find position. Again, Heisenberg's uncertainty principle and just the general probabilistic nature of quantum mechanics. All quantum mechanics has to offer is statistical info about possible results. So this brings up a philosophical debate. Is it a fact of nature or is it a defect in theory? So there's many different ways of interpreting the wave function, but the most famous one is the Copenhagen interpretation, where we consider that the particle is in quantum superposition, and only when we interact with it, such as like take a measurement or operate an operator on the wave function collapses down onto a single position C. So essentially observations they don't disturb the particle's measurement. They don't disturb the measurement of the particle or its aspects. So if we have a wave function and we view the square of the wave function, as soon as we interact with it or take a measurement using an operator like the Hamiltonian, the wave function collapses down to a single point. And because of that, there's two physical processes: the psi evolving under the Schrodinger equation and the psi collapsing during the measurement. And that's the Copenhagen interpretation. And